Lying just beneath everyday reality is a breathtaking world where much of what we perceive about the universe is wrong. Physicist and best-selling author Brian Greene takes you on a journey that bends the rules of human experience.
Why don't we ever see events unfold in reverse order? According to the laws of physics, this can happen.
It's a world that comes to light as we probe the most extreme realms of the cosmos, from black holes to the Big Bang, to the very heart of matter itself.
I'm gonna have what he's having.
Here, our universe may be one of numerous parallel realities. The three-dimensional world may be just an illusion, and there's no distinction between past, present, and future.
But how could this be? How could we be so wrong about something so familiar?
Does it bother us? Absolutely.
There's no principle built into the laws of nature that say that theoretical physicists have to be happy.
It's a game-changing perspective that opens up a new world of possibilities. Coming up, the realm of tiny atoms and particles, the quantum realm. The laws here seem impossible.
There's a sense in which things don't like to be tied down to just one location.
Yet they're vital to everything in the universe.
There's no disagreement between quantum mechanics and any experiment that's ever been done.
What do they reveal about the nature of reality? Take a quantum leap on the fabric of the cosmos right now on Nova.
Major funding for NOVA is provided by the following: David H. Koch and
Discovering New Knowledge. HHMI.
and by the Corporation for Public Broadcasting, and by contributions to your PBS station from viewers like you. Thank you. Major funding for the fabric of the cosmos is provided by the National Science Foundation, where discoveries begin. And the Alfred P. Sloan Foundation, supporting original research and public understanding of science, technology, engineering, and mathematics. Additional funding is provided by the Arthur Vining Davis Foundations, dedicated to strengthening America's future through education. The U.S. Department of Energy's Office of Science, and the George D. Smith Fund.
For thousands of years, we've been trying to unlock the mysteries of how the universe works. And we've done pretty well, coming up with a set of laws that describes the clear and certain motion of galaxies and stars and planets. But now we know, at a fundamental level, things are a lot more fuzzy, because we've discovered a revolutionary new set of laws that have completely transformed our picture of the universe. From outer space to the heart of New York City to the microscopic realm, our view of the world has shifted thanks to these strange and mysterious laws that are redefining our understanding of reality. They're the laws of quantum mechanics. Quantum mechanics rules over every atom and tiny particle in every piece of matter, in stars and planets, in rocks and buildings, and in you and me. We don't notice the strangeness of quantum mechanics in everyday life, but it's always there if you know where to look. You just have to change your perspective and get down to the tiniest of scales, to the level of atoms and the particles inside them. Down at the quantum level, the laws that govern this tiny realm appear completely different from the familiar laws that govern big, everyday objects. And once you catch a glimpse of them, you never look at the world in quite the same way. It's almost impossible to picture how weird things can get down at the smallest of scales. But what if you could visit a place like this, where the quantum laws were obvious, where people and objects behave like tiny atoms and particles? You'd be in for quite a show. Here, objects do things that seem crazy. I mean, in the quantum world, there's a sense in which things don't like to be tied down to just one location, or to follow just one path. It's almost as if things were in more than one place at a time. And what I do here can have an immediate effect somewhere else, even if there's no one there. And here's one of the strangest things of all. If people behave like the particles inside the atom, then most of the time, you wouldn't know exactly where they were. Instead, they could be almost anywhere until you look for them. Hey, I'm gonna have what he's having. So why do we believe these bizarre laws? Well, for over 75 years, we've been using them to make predictions for how atoms and particles should behave. And in experiment after experiment, the quantum laws have always been right.
It's the best theory we have.
There are literally billions of pieces of confirming evidence for quantum mechanics.
It has passed so many tests of so many bizarre predictions.
There's no disagreement between quantum mechanics and any experiment that's ever been done.
The quantum laws become most obvious when you get down to tiny scales like atoms. But consider this. I'm made of atoms. So are you. So is everything else we see in the world around us. So it must be the case that these weird quantum laws are not just telling us about small things. They're telling us about reality. So how did we discover them? These strange laws that seem to contradict much of what we thought we knew about the universe. Not long ago, we thought we had it pretty much figured out. The rules that govern how planets orbit the sun, how a ball arcs through the sky, how ripples move across the surface of a pond. These laws were all spelled out in a series of equations called classical mechanics, and they allowed us to predict the behavior of things with certainty. It all seemed to be making perfect sense, until about 100 years ago, when scientists were struggling to explain some unusual properties of light. In particular, the kind of light that glowed from gases when they were heated in a glass tube. When scientists observed this light through a prism, they saw something they'd never expected.
If you heated up some gas and looked at it through a prism, it formed lines. Not the continuous spectrum that you see projected by a piece of cut glass on your table, but very distinct lines.
It wouldn't give out a smear, kind of complete rainbow of light. It would give out sort of pencil beams of light at very specific colors.
And it was something of a mystery how to understand what was going on.
An explanation for the mysterious lines of color would come from a band of radical scientists who at the beginning of the 20th century were grappling with the fundamental nature of the physical world. And some of the most startling insights came from the mind of Niels Bohr, a physicist who loved to discuss new ideas over ping pong. Bohr was convinced that the solution to the mystery lay at the heart of matter, in the structure of the atom. He thought that atoms resembled tiny solar systems, with even tinier particles called electrons orbiting around a nucleus, much the way the planets orbit around the sun. But Bohr proposed that unlike the solar system, electrons could not move in just any orbit. Instead, only certain orbits were allowed.
And he had a really surprising and completely counter-physical idea, which was that there were definite states, fixed orbits that these electrons could have, and only those orbits.
Bohr said that when an atom was heated, its electrons would become agitated and leap from one fixed orbit to another. Each downward leap would emit energy in the form of light in very specific wavelengths, and that's why atoms produce very specific colors. This is where we get the phrase quantum leap.
If it weren't for the quantum leap, you would have this smear of color coming out from an atom as it got excited or de-excited. But that's not what we see in the laboratory. You see very sharp reds or very sharp greens. It's the quantum leap that's the origin and the author of that sharp color.
What made the quantum leap so surprising was that the electron goes directly from here to there, seemingly without moving through the space in between. It was as if Mars suddenly popped from its own orbit out to Jupiter. Bohr argued that the quantum leap arises from a fundamental and fundamentally weird property of electrons and atoms, that their energy comes in discrete chunks that cannot be subdivided, specific minimum quantities called quanta. And that's why there are only discrete, specific orbits that electrons can occupy.
An electron had to be here or there and simply nowhere in between. And that's like nothing we experience in everyday life.
Think of your daily life. When you eat food, you think your food is quantized? Do you think that you have to take a certain amount of minimum food? Food is not quantized. But the energy of electrons in an atom are quantized. That is very mysterious, why that is.
As mysterious as it might be for tiny particles in an atom to act this way, the evidence quickly mounted showing that Bohr was right. In more and more experiments, electrons followed a different set of rules than planets or ping pong balls. Bohr's discovery was a game changer. And with this new picture of the atom, Bohr and his colleagues found themselves on a collision course with the accepted laws of physics. The quantum leap was just the beginning. Soon Bohr's radical views would bring him head-to-head with one of the greatest physicists in history. Albert Einstein was not afraid of new ideas. But during the 1920s, the world of quantum mechanics began to veer in a direction Einstein did not want to go. A direction that sharply diverged from the absolute definitive predictions that were the hallmark of classical physics.
If you asked Einstein or other physicists at the time what it was that distinguished physics from all kind of flaky speculation, they would have said it's that we can predict things with certainty. And quantum mechanics seemed to pull the rug out from under that.
One test in particular, which would come to be known as the double-slit experiment, exposed quantum mysteries like no other. If you're looking for a description of reality based on certainty, your expectations would be shattered. We can get a pretty good feel for the double-slit experiment and how dramatically it alters our picture of reality by carrying out a similar experiment, not on the scale of tiny particles, but on the scale of more ordinary objects, like those you'd find here in a bowling alley. But first, I need to make a couple of adjustments to the lane. You'd expect that if I roll a few of these balls down the lane, they'll either be stopped by the barrier or pass through one or the other slit and hit the screen at the back. And in fact, that's just what happens. Those balls that make it through always hit the screen directly behind either the left slit or the right slit.
The double slit experiment was much like this, except instead of bowling balls, you use electrons, which are billions of times smaller.
You can picture them like this. Let's see what happens if I throw a bunch of these balls. When electrons are hurled at the two slits, something very different happens on the other side. Instead of hitting just two areas, the electrons land all over the detector screen, creating a pattern of stripes, including some right between the two slits, the very place you'd think would be blocked. So, what's going on? Well, to physicists, even in the 1920s, this pattern could mean only one thing: waves. Waves do all kinds of interesting things, things that bowling balls would never do. They can split. They can combine. If I sent a wave of water through the double slits, it would split in two, and then the two sets of waves would intersect. Their peaks and valleys would combine, getting bigger in some places, smaller in others, and sometimes they'd cancel each other out. With the height of the water corresponding to brightness on the screen, the peaks and valleys would create a series of stripes and what's known as an interference pattern. So, how could electrons, which are particles, form that pattern? How could a single electron end up in places a wave would go?
Particles are particles, waves are waves. How can a particle be a wave? Unless you give up the idea that it's a particle and think, aha, this thing that I thought was a particle was actually a wave.
A wave in an ocean? That's not a particle. The ocean is made out of particles, but the waves in the ocean are not particles. And rocks are not waves. Rocks are rocks. So a rock is an example of a particle, an ocean wave is an example of an ocean wave, and now somebody's telling you a rock is like an ocean wave. What?
Back in the 1920s, when a version of this experiment was first done, scientists struggled to understand this wavy behavior. Some wondered if a single electron, while in motion, might spread out into a wave. And the physicist Erwin Schrödinger came up with an equation that seemed to describe it.
Schrödinger thought that this wave was a description of an extended electron, that somehow an electron got smeared out, and it was no longer a point, but was like a mush.
There was a lot of argument about exactly what this represented.
Finally, a physicist named Max Born came up with a new and revolutionary idea for what the wave equation described. Born said the wave is not a smeared out electron or anything else previously encountered in science. Instead, he declared it's something that's really